Okay, it's time to be back. Um, so now we can go over the process that I was talking about during my presentation. I post on the chat some SANS data for those persons that don't have their own data. So you can use I think the most ways we do this interactive is that I'm gonna open my raw window here and show the process to you all. So how you analyze and how you interpret. There is a little bit more information that you can look in the data. It's not only the presentation is kind of fast for you to look at, but it's good for you to have the raw window. So I may ask everyone has the raw window style raw could install the raw in Pymol or Chimera. So I can show you how to look at those data and how to load structures. And also it's going to be important to have the HSAC spec page installed because it's where we have the Quaison and Gnome to do the sketching profile calculation and also the uh, scaling profiling calculation and a PFR determination. Let me see. There's something in the chat. Let me see. Or now account. That is a little bit surprise. Let me see. I was not expecting for that. Okay, can you type? Everyone could get the data. Only Antonella and Garcia could not. Okay, so if you guys type our email very fast on the link, I can share the data. Please, you'll do my best to share with everyone. I was expecting to share the data with you all here. Okay. That worked before. Yeah. Okay. Antonella. So the recordings, we will separate them in different presentations, and then we can share them. Probably we're gonna send an email with links so we can access, and also made them available on the web page of the conference. Okay, let me see. I have here Gmail from Jacob. Um, give me just a second.
Having trouble with the link to the file?
Yeah, they don't. They is asking our now account, so I'm getting their email so I can send
Okay.
them. It's not a lot of people. That will be fast.
Okay, I guess that's something to learn for the next time, right?
Yes. Check. But I haven't shared before here. I don't know what happened. Maybe because Okay, almost there. Lorena. Yeah, I have one. I have the Jacob, Yuk, Antonella, Adrish, Priyanka. Okay, okay, that's yeah, Ashman. Okay. If I'm missing one, please let me know. I just send email. You got it? Okay. Yes, you have to unzip the file. Thank you, Ugly, for sharing the data. Okay, so let's start. If you don't receive any mail, let us know so we can help you provide the data. So I'm gonna invite Vishwanatha. He's a graduate student here with us, so he can help us with solving those issues, and also
I can do that for you,
you can
Wellington.
okay.
Yeah.
Okay, let's start it then. The folder that I share with you all, uh, there is different folders on the zip file that I have shared. So let's start with the empty cell subtraction, which was the first step that we work on the data. So basically, what we want to do is load this data on raw, so we can start doing data analysis from there. You can copy the path of our file. Once you have the raw open, you can just paste the path here, or you can looking for it where it is in your computer. So either works. And here's I already have the data there placed. Um, let's start loading first of our empty cell, which is the run number 1644. So this is the data that we collect for the empty cell. Uh, and so empty cell, I mean, it's just a bunch of cell of with no buffer or anything. And we load now our next sample, which is the buffer. Okay. And the next one is the protein data. Okay. So you see you have different sketching profiles. You have definitely much lower scattering for our empty cell. So you can look how is the behavior in the low Q region. So is where we have more scattering from the empty cell, but is similar from protein buffer. And the high Q region of our buffer is a flat region, so is most like contribution of the incoherent scattering. And you also have the scattering of our sample, which is here. You have proteated sample, the HSA was proteated, and you are looking to sample in a fully dotted buffer, which is 100% D. So the 100% D in my labels here uh, uh, stand for the duration of the buffer, not the sample. Okay. I click look on ROS window here. The way that we start is we have our buffer. Okay, our buffer. And you do the first step is do the subtraction. You are removing the contribution of the empty cell from the buffer. So doing so, you mark the star here on the top right side of the when you make the you select both buffer and empty cell, and you're gonna subtract the data. If it doesn't show up for you, you just click in the button home and you can see. So in the right side where we load our data, raw give us some flexibility to analyze this data in different kind of plots. So here I'm using a log plot, but you have options also to do a linear plot, which is a little bit hard to visualize the data. In general, is not the way that we analyze this data. We like to do a log plot, so you have different types of plots you can do here. As you see, Guinea plot also can be done here. It's not where you do the Guinea analysis though. You do the Guinea analysis using different filtering software. Crack plot is where you do here in Parod. And okay, let's go back to the log and home to show all the data back there. So in the bottom we have log link. So I want everything in log. So this is the subtracted data from my buffer. We can definitely compare and see if my subtraction, see if I remove the contribution of the empty cell of my data properly. And now, like I say, in general, this step we do in data reduction. So uh, we using has a background during the script. We run the script with data reduction, use the empty cell as a background because we are removing all background contributions that is it's present in our data in that step, having the instrumental contribution that can be present there. So you are removing use the empty cell. And the idea is that you're just going to remove the contribution of our buffer uh, to the sketching of the sample. And next step, you're going to remove the empty cell subtraction from the sample. Okay, so this is how it looks like. If you see here, that is more high Q, low Q here of the buffer. It's still going up, uh, increasing the intensity and the low Q. You can analyze, which is more close, I'm gonna hide the sketching of the sample, okay? And I'm gonna hide the sketching of my protein there. And I'm gonna look at the low Q here. I can give a zoom, look at the low Q of the empty cell and buffer. So basically the buffer empty cell should not have sketching at all at the low Q. They should match at the low Q. Both sketching contributions should be very similar, except the buffer has a little bit more sketching than the empty cell itself, as we see here. But the very low Q, they should be very similar. So the way to correct it is buffer. You can scale the empty cell uh, for one given number. Let's start at 0.1, and that way you are scaling right. You see now the empty cell starting going close. Maybe it's too much. Let me see. Yeah. Now they are matching very well, so you can do the subtraction and see how it looks like. Oh, I did against the wrong sample, sorry. It's buffer empty cell here. Now the sketching of the buffer more looks like more what we expect to see, flat line. So there's no much scattering the low Q for the buffer, and we have a flat line on the high Q. So that scaling factor does not gonna really affect the high Q. It's only the low Q regime. So you are here remove any parasite sketching or the sketching from the background from the instrument as well. So we are correcting of our data. So if you look at the sketching for our sample, we don't have that issue. It's kind of nicely go flat in the low Q. Okay.
Wellington,
Yes.
can I make just one comment? Because you hit on something very important there.
Yes, I cannot hear you, Volker, very well.
Oh, down. Can you hear me better now?
Yes.
So it's a scale factor that's applied, and when you showed the low Q region of the empty cell and the buffer in the magnification, there's something very clearly that you can see that it's a factor rather than a constant because you're in a log scale. I don't know if you can make that, if you can do this again. When you zoomed in there before you scaled it up, you could see that there was basically, yeah, if you put this back to 1, exactly. So if you look along this curve, you can see that you basically have a constant offset between the two. But a constant in a log scale, of course, is a factor. So so that kind of tells you that you're off by a small factor, and that can happen with normalizations. So it's something that's within the expected uncertainties that you can have in the normalization process. So that's why you have a very good physical reason here for scaling, for applying small scale factors. If it's off a lot, then that would be a concern. But I think you had a few percent in there as a scale in your scale
Yeah,
factor.
0.5.
So that can commonly happen. So I just thought I'd point that out because it's very significant when you look at this. You can see this if you have a little bit of experience. You can see what's happening here. So go ahead.
Thank you, Volker. Yeah, I appreciate. Okay, so now we did a small correction of our data. So just in case, let's assume you're not gonna do it this correction, right? It's good to show the worst case scenario as well. Let me put back there. I maybe have too much things here. Let me put back there. You have our HSA, you have our buffer, and you're going to do one-to-one subtraction. I think the scaling factor is 1-to-1. So you're going to structure the empty cell. Okay. So, and then you have our data here. That contribution can corrupt our data in the low Q. Let me do here very quickly. I'm going to do the buffer. Subtracted, yeah. Open, no. Yes. So that contribution can definitely be an issue for you there to subtract our data and can impact our data in the IQ because we are subtracting too much here. So even though we don't really gonna see, we don't have much data there, so our useful data because of the size of the protein is, so in the low Q we are try get a fight with signal to noise, so we need to definitely increase to longer the statistics to much longer time to make sure you get good data here. If you use that you not correctly, you're not gonna get right subtraction. So it's good to have the double check how is the empty cell there. So I'm not need this data here. Let's see the data that we use here. So now uh, I did my subtraction already. I'm gonna hide those data that I don't need, and I'm gonna move to the top plot. Uh, there, my empty cell subtracted data. So, and here it's a common observation that we see on the sun's data. The high Q of our sun's data does not match with the buffer. So if you have the uh, ideal buffer where everything is perfect fine, you have the right amount of D2O in your sample and your solvent, in your buffer in your solvent, you should expect the high Q regime to be match. But there's some effects that happen that sometimes you don't have the same concentration of D2O in both. They are slightly different. And there is other effects of the incoherent scattering, the high Q, that there is a mismatch between the buffer and the sample. So if you do a one-to-one subtraction, I'm gonna use the buffer, which is the red curve. Okay. You see your data in the high Q is there's a flat line there. That tells you you still have to remove some incoherent scattering that is present in your sample. So our sample, the information that we have there is the coherent scattering that come from the interaction between the neutrons with our macromolecule, but also have the incoherent scattering that there is no information at all. That is other type the interaction that happened with the those macromolecules that is not gonna give you data, is gonna give you more noise on the phenol scattering profile. So the way to correct it for this difference here, you can see is also there is a small mismatch on the data. You can apply uh, constant factor to multiply the buffer scattering profile, and you can correct it for those difference. Um, that
Wellington.
is the practical way. And sometimes if you know that what is
Wellington.
the the difference in D2O on the development fraction of D2O in both sample and background, you can do just correction more precisely if you know that what is the difference. But in general, the difference between the level of this. Hmm?
Wellington, can you increase, please, the size of the window? Maybe that helps.
That helps.
Let's see. Is it better, Shalika?
See if I can do it like.
Yeah, I think yeah, now it's good. Uh,
It's
yeah,
better.
yeah, now it's good. Yeah, it's better.
Okay. Yeah, let me know if I have any issue. Is everyone able to do this process in your own computer? That is important. So you have to get a feeling how to do those things. If I'm doing too fast, please let me know as well.
I think I'm a little behind in what it is that you're doing. So for the things that you subtracted, can you go over what you subtracted from what again? I think I missed that.
Okay, so let's move one step back then. The first step is for you to do the subtraction of the buffer and sample, right? Buffer and protein HSA against the empty cell data. So you are doing the first correction of your backgrounds, removing the empty cell contribution. So this is the first step. So just I'm gonna put there very fast. I don't mind to do very fast. And you see you have the 3 sketching profiles there, right? And you can zoom in here, and you need to scale your empty cell from a scale factor for you to correct the low Q data of our buffer, which it has a little sub difference there. And the results of these subtractions is where sample and buffer, which is in the top plot right now. On the top plot, and then we are doing the subtraction now of this sample and buffer, correcting now the background of our solvent. Did you got it?
Yes, thank you.
Yeah. So Vishwa, you're here.
Yeah.
You're muted.
Yeah, I'm around. Yeah.
Okay. If you have any questions, you can also post in the chat, and Vishwa can help you off the in a separate conversation of the teams in another window, so he can help you to go to over this process. And now that we have the data already on place, we're gonna correct it for the difference between the sketching of the buffer and our sample. So we're gonna scale up the buffer. Let's see how much we need. So we can use the scaling factor is here on the left side of the green when you selected the war buffer. So we're gonna again mark the start to do the subtraction again against the buffer. And let's say that we're gonna start from 0.0, maybe 0.8. It's a number that I know that is kind of okay. So you can tune this parameter to scale it to higher numbers or lower numbers. Raw allows you to do just scaling very easily here, moving up and down. And you can subtract the word data. Let's see how that looks like. Okay. A home, and you see, let's compare to 1-to-1. So the gray one was 1-to-1 subtraction. You see we have a flat line, and now our data is going more towards the what we expect to see for a protein, like Volker said yesterday on his meeting, on his talk, that we have Q2 -4 here in the case of you have a globular structure, and you see the dependency for proteins also is present there. Here is one step where you can check if your background subtraction is going okay. You see the high Q going with a parallel Q2 -4 to the high Q region here, but you can also do, like I say, that crack plot. Let me do that. So you're gonna click with the right side of the mouse in X, and you say crackling. Okay, let's just do some adjustments that you can also do here. We have now the IQ chi-square by Q, which is the cracky plot analysis that I told you that we can tell us about the conformation, but also help us to do the background subtraction. It's kind of guide that help you to define how much background you need to remove of our sample. Here, when I like to do is make that very clear. So I click with the right side of the mouse on axis and plot options. And you can x 0. You can put this data on 0. Let me see what's the scale that I want to go to. I want to go to 0.05 in the IX. Okay. All right. So if you see, if you remember of my presentation, does not look like we are going smoothly to the high-Q regime with our crackle plot analysis. So if you want to remove more background of this data, this is the case. We know the HSA is global, right? We know the HSA it's folded, so we expect this to go smoothly to the high-Q regime here. And we need to remove more background. If you have a disordered structure, one intrinsically disordered protein, for instance, just that is not going to have this bell shape, it's going to be more flat line in the high Q region here, is what you should expect for globular non-structured protein. Okay, it tells me that I need to apply more background. I'm going to be a little bit cautious here, but just increase to 85 and do the subtraction. Okay, I can move a little bit more further. Let me see if it don't do too much. No, it can be more aggressive, a little bit more. So the good thing of raw deck is saving for you here all the profiles that you are subtracting. So you can compare them and see what is the one that is useful or not for you. And I think we are almost there. Let me do just a little bit more. Okay, we are HSA buffer, HSA. Yeah, that is kind of okay. We don't need those other profiles anymore because they are definitely not good background subtractions. We can select all of them and remove it.
Wellington,
Yeah.
there is a question from Jacob. He wants you to restate what is the purpose of tweaking or scaling during the subtraction.
The reason is that Jacob, in the IQ, I'm gonna put it one by one again. The high Q region of war buffer and sample, they are not matching. So that tells you that there is some mismatching between our buffering and our sample that need to be corrected. So there is several things that can cause this issue, but the most common issue is the difference for the SUNS data is the difference of the how much G2O you have in your sample and how much G2O you have in your buffer. So the scattering in the high Q is mostly doing the incorrect scattering. So when you have those differences on the high Q, especially when you have D2O present in your sample, can cause a mismatch there. So this mismatch, if it's not huge, can be correctly using the scaling factor like I'm using here. So you just are moving up in uh, the the buffer background has you are just increasing the incoherent scattering that is missing on that sample. So you can also have the other way around. You can have, or for instance, I'm gonna exaggerate here. You can have, okay, you may have something like that. So where buffer be higher than war sample is also a possible mismatch. Does that answer your question?
Yes. I'm curious what you would call an acceptable amount to correct this way instead of having to, I would assume it would be a remix of your buffer or your sample to get your D2O proportions right. But like how much can you wiggle around in here before you're starting to make too large of a correction?
That is a
Under
good question.
under 10%, under 20%?
I think that the way that I usually do with 10%, it's some residual looks like a number that makes sense, but it can be a little bit higher, depending of how much was the mismatch, right? If the only effect of this mismatch is doing because of uh, the difference between the level of T2O, so you can, the way that you can detect this is you can look at the transmission of our sample and buffer. So if they have a huge difference in the transmission, it doesn't mean you have definitely a difference on D2O, on the level of D2O. That is not really, you cannot really make a judgment of you can use the buffer or not, even though it's just a scaling move up and down. But if the transmission, they are kind of similar, you kind of know what is the difference and you can kind of guess how much percent you can scaling or scattering of for either sample or buffer.
Okay.
Preferring the buffer. The ideally should scaling the buffer.
Okay. That makes reasonable sense. Thanks.
Okay, now we have the subtract to our background. We can definitely go back to our log plot. Okay, so we have here then on the top plot where unsobstructed data, and then we have the bottom plot with the substructed data. We can start doing the analysis now. We can look over this data and see what we can get from here. So if you are worried about the how you are visualizing your data, you can definitely tune your scaling on the I-axis and the X-axis as well. I'm just gonna open. I can see the local data very well. So if you look at the data here, we can see that we almost have our data. We have our data with a nice plateau here in the local region. That tells us that we can calculate very nice the Guinea region of the calculated Guinea, do a Guinea analysis of our data because our local is flat, right? If you remember from Vox talk yesterday, if your data is starting to increasing the local, it's mean that you not reach the Guinea region and you cannot properly apply this analysis. So the way that we look at this data is that our data collected is flatted on the local. Uh, uh, like I say, we have huge error bars here in the region because of the size of my protein, giving me scattering, not giving a good scattering, not give Q range. So my low Q data here, I need to definitely collect much longer data for much longer times to get good statistics at the low Q. Which is maybe you don't need it. You are here. I use a long configuration to collect this data, but a short configuration is 7 meters, 6 angstroms could give me the reasonable good data from this experiment here. Let's see, do the Guinea here. So click with the right side of the mouse and do the Guinea. Okay, so here's the trick part. We can play a little bit. I hope that you can see my screen. So raw automatically does calculate a Guinea for you. It applies some Monte Carlo method to do this initial fitting here. And you can definitely tune the Guinea fits, and you have to and look what's the best fitting for you. Again, for local data, you see some points there are really not is not give you any information because they are most noise of in the local. You can still go over your high Q towards your high Q region. You see your Q by RG is still low, not greater than 0.65, so you are okay. And the RG from this fitting here is 24.2 0.3, and the I0 is 0.1519. So in that situation here, you can also go to fit in the high Q, the high Q regime of the Guinea analysis. Right now, the high Q, you can move or fit into high Q, and you see that I haven't go to 1.85. I kind of have a nice linear fit of our data, but I'm out of the limits of the Guinea regime here, so I should be back to lower than not greater than 1.3. So with that, you can save this data here. You can export as a CSV file, so you can plot it in any other software. On my folder, you find the Guinea analysis plot there. Is already saved on the folder. So you have the Guinea analysis there. You have those out of those informations. The normalized residual plot has a CSV file, and also the Guinea fit with the data points from the fitting. So the only thing that raw does not do here is the error bar calculation of the fitting, unfortunately. But you can definitely do it off raw and get the error bars from where we're fitting. Are there any questions? Okay, so if you finish your Guinea analysis, so what is going to be the next step? You look for the P of R calculation. It's also so probably when you did the installation of HSAX, which is the other pack page that I told you, you can check if your raw was able to find the path of HSAX. So it's important. Otherwise, you cannot do this analysis there. And you can look here options and advanced options. Okay. Go to HSAX. And the path for HSAX should be set up there. That way, raw can load the softwares that he needs to do the calculation for you. Okay, please check if you have there. If you had that there. Just very quickly here, we are already into the screen. If you see, we have here from HSAX raw the genome. That is for the regular genome for macromolecules, for more globular particles. But you also have different kind of P of R calculations that you can use. There are different types here, and depend of the system that you are using, so you can you can change the type of the probability distribution function you are using, selecting different kind of P of R types of PR they want to use. For instance, if you have cross-section number 4 cross-section distance distribution of Monod pairs Hodge-like particles. When you have more elongated particles, you can determine the probability of the distance for the cross-section part of the structure. And also you have the ab initio software for ab initio determination here. You'll be using different softwares in this process, but the main one is the Demuth and Demuth and Demuth. Demuth does the average of the ab initio reconstructions for you, and SupComp does the superposition, like I was explaining on my talk before. And you also have dense, which is those ab initio reconstruction using a different method that is more like in this case here for Sax is electronic density reconstruction of the sketching from using the sketching profile. Okay, let's go back to the PFR. Okay, so we click with the right mouse, FT GNOME. So raw is gonna try give for you again when you initial guess of how looks like the PFR. So you can definitely adjust the points where the data is to noise. You ideally, like I say, you need to use you can use the full key range to analyze the data. But if it's not the case, you don't have the full key range there, you can decrease your range here, the Q maximum, right? You start to see the PFR already starting getting a nice shape. And so one good thing about raw is that the Q minimum used to do our G calculation, raw is already gonna pick for you to be your Q minimum to start your PFR calculation. Uh, let's see now. You can start adjusting your D maximum. Okay. Okay, it's not a good solution. Go back. See if they remove those noise points here. I can definitely go for. So this is the good one. Let me see if I can get a bit more. I got 82 yesterday. Yeah, you see, that is definitely is not a good solution for PLFR. You could not have negative values in the for higher radius here for higher distance, so you can trigger a bit more. That is definitely much better. You see, it goes smoothly to 0 in the longer distance is what we expect to see. There is no a lot of oscillations of our P of R. Let's us now trick for lower distance here. Okay, I think that is better. Definitely, yeah, that is a good P of R. You have good, so the 0 is all starting 0. You don't have a shift. And the other way to do that is that here I'm forcing my PFR to go to 0 at the D maximum. You can ask for not force, and you try fit the data. That's probably a good solution there. You see, goes smoothly to the 0 and does not oscillate. So when your PFR is oscillating too much, you have a problem in your data, problem in the background subtraction, or was done maybe too much. And you can see, but here you already have a good PFR. That should be your the maximum of the cal the protein that we are calculating. So if you finish your PFR calculation, you see the Guinea region here with your I0 and P of R with I0 as well, determined using the P of R calculation. And you have the key range you are calculating. Oh, sorry. You have the key range you are calculating the P of R here, and you can just say okay. Okay. So after you say okay, you have our IFT here, which is gonna show for you here. IFT is the P of R calculation. You can see here is already normalized by I0. So in general, if you have different P of R's, there's different normalizations that you can use to compare our P of R profile. And one of them is normalized by I0 that raw already does doing the calculation, but it's common, it's necessary, it's necessary you normalize by the area of the P of R. So basically the area is proportional to the number of particles you have there. So when you normalize everything for the same area, you are normalize the P of R by the number of particles, and then you can do a directly comparison. Uh, of the PFR profile. So you can save this data here. Okay, you can save this PFR. I think I have done. Yes, it's there. I saved there. You can definitely use the genome output for the ab initio reconstruction later on. It's not what I'm going to do now. Let me see. Okay, I'm not gonna save. What else? Let me see. Cracky plot that we don't see the cracky plot. Let's go back for profiles, and you can now we can do the dimensionalis cracky plot here. Okay. Here is really good to do comparisons, like I say. So we will eliminate the size dependency and we only see the conformation. As like I said, you can see there is for globular particles, you see a maximum uh, of the cracky plot around 1.1 and in around 1.73 on the Q by RG axis is the deposition where we should expect. And when you start to see deviations of this position is because you are through some flexibility in your system. So it's a good way to compare different scattering profiles and see if you have the sample in different, for example, in different conditions, if there is any conformational changing happening, it's a qualitative way to check that. Okay, so you have done all of this. You want to know, okay, how can I options view? That is to save a report. You can save a report, HSCA data. EFT, okay. So you can definitely combine all you will have done now for the subtraction data. So here you can see that we have the sub2s, that it means that data was subtract twice, right? One for the empty cell and the other from the buffer. I can definitely save a report of this in PDF. It's only PDF, yeah, it's only PDF. Save a report, files, shop, okay, raw report. Save there. Let's have a look. Okay, so basically, you have there or sketching profile. It's the raw. I think raw now is not saving the log scale, but definitely you can trick that to adjust those to saving log scale. You have our Guinea analysis there with the residual here on the plot. The correctly plot information and the PFR calculate from the sketching data. And you have a summary of our results here. It's going to give you the Guinea RG and Guinea genome, and for you to do the comparison. And definitely, and here you have a more detailed information of what Q range you use for the genome and the R square of the fitting, how good there was the linear fitting for the RG. And here's the genome as well, with the output of the genome. Okay, now let's go back to raw. I just want to show one more thing. Yeah. So if you have done all of the steps, right? The next step for you is if you are in raw, you can do the build model or the ab initio right here. Okay, I'm gonna click here. Is that you can do some put parameters here. It's gonna use that file for you to the output the PFR from the HSA, and it's gonna save on that folder. You can select where you want to save. Let's see. I'm gonna just do ab initio modeling. HSA. Sure. You select your folder. So here is you're gonna tell the number of reconstructions if you are running. You can run in parallel um, how different numbers of reconstructions, and so my experience in raw it's a little bit time consuming run them here. I prefer using the uh, AT-SAX directly to do that. So I'm just gonna call here. You can use the SAX data analysis, which is the software. I'm gonna do just side by side. You can have one idea. Let's load the raw the AT-SAX data there. Okay, we did buffer subtraction, so this is our subtracted data. Okay. So you have CT's window on my presentation, right? So you have in the it sucks you have where you can do average subtraction and scaling of our data, and you have the tab for analysis. Here you have the rates of variation as well, P of R power distance distribution, P of R calculation, which is also using the GNOME, and you have DEMF, which is the software that I'm telling you. I think here is more low to run the software than run here. I think there's some ways that the how it's implementing on both software is different. So you have faster results using the Primus, so it's not so time consuming when you run on the raw. So just gonna click go over here. We can do a manual selection of the parameters. Okay, first thing is gonna ask you to do the Guinea fitting. So you can definitely adjust the Guinea fitting here. Now use the local data. So we are showing the Guinea limits. It's very similar what I got before. The I0 as well. Okay, I can just move next. Okay, let's get the PFR here. I'm not gonna be, that's not good. Go back. Go back. Okay, I'm not gonna use all points in the low queue. Let me see, yeah. Yeah, definitely is there. Was too long. Okay, so I calculated my PFR profile, and now I can go next. So the way that Primus does this is gonna ask you to do a fast or slow calculation. I think here is just how much memory of our computer is gonna, how much resource of our computer is gonna be using. In general, I do a fast that model that I show on my. Let me go back there. This model here, I did using the fast, and I could get a nice shape of the HSCA here. So definitely, if you want to do a more refined, you can definitely use more. You can do more repetitions. You have more. Uh, uh, how many models you're going to generate. So basically, the idea is that them if it generates different kinds of those BD models for you, and afterwards the Maver or the average software that he uses is going to average out those BD models to give you the overall shape. So you can use the number of repetitions you want here. 10 is just fine. If if you have some symmetry in your for data, you know that symmetry. For instance, you have a hexamer or a trimer, you can apply the symmetry here and get the right all the way you get the right shape that you expected. If your data is kind of looks like more oblate or pro-8, you can also adjust that, so you're gonna gain more or whatever. And the angular scale, you don't need to worry about that, because generally if you have a nanometer, where data is gonna already show for you what is the angular scale, and then the Primus can just get that. He's very fast. You just clicking commit is gonna start for you the calculation. Is like I say, it's faster than using here than do the in raw. But if you don't want to do, you can definitely go on raw and see what is the requirement. Is kind of similar. You have what software you are using. Them if it's just a more uh, um, fast way, then does them if it's the calculation is similar, but does this them if it's a little bit faster. And it's gonna you have to ask average UR envelopes using the mover and refine it, then use the mean here. And if you know that what is the PDB, you can already ask here to do the alignment for you. So the raw is going to align your PDB structure with our envelope. So the tricky part is how you visualize this envelope on any other software you want to visualize. Okay, I think I'm not gonna let it run. I'm gonna abort here. I don't need to show. Basically, yeah, the results are coming there. Let me show you my folder, what you should expect to see after you done with ab initio. Yeah, if you go to the folder I send you in the ab initio folder, you have the outputs for them. You see I have 10 reconstructions there, 10 reconstructions. So it starts 12 6 and was 12 12 12 12 12 24. They took less than 20 minutes uh to do the entire reconstruction, so it does not take longer. So if you have the PyMol open or installed in your computer, you can look what is the final shape you are looking for. So you see just the output file here. You have different files, right? You have our hsax, which is the sketching profile. Let me open that very quick, which is our sketching profile. So he's doing the calculation, and you have the fitting of the P of R for that data. And here you have the fitting of our model. And you should have a PDB here, yeah. Open. Oops, is there. Okay. So yes, so here you cannot really see anything the way that it's showing for you. You can ask to show has spheres and hide the ribbon. Yeah, right ribbon or hide cartoon. Yeah. So basically, what I'm seeing here is in the first model that was reconstructed in the BID model. You can definitely overlay already your crystal structure of this ab initio model here. I personally like to use Chimera to do this. I'm just show here is my computer just show very fast the PyMol section. Let's see in Chimera and what you should be looking for. So okay, Chimera. Okay. So if you look in your folder, the final file you should looking for after the results comes out is the then filt is after the everything was processed. So the final file that have the war ab initio reconstruction shape done is the file. So we're gonna look in Chimera on this file. I'm gonna just copy the path. I'm opening back my Chimera. Are there any questions? No. Open. Okay. Field it's the PDB. Okay, again, does not look nothing that is interesting, but let's make that difference. So you can come here in tools, control, command line. You probably have the command line on War Chimera. If you, I'm not sure what version of Chimera you have, but it's similar. You may have a command line on the bottom side of the Chimera. Let's transform this to a map. So the command for transform the ab initio reconstruction to a map is small map. You're gonna call the model number, which is 0, and you're gonna see what's the level of reconstruction of this map here, which is around 30 angstroms around the structure. And okay, so basically what I did there was to turn my Benitian reconstruction. I can show how was the bid in the bid structures is what we expect. I'm just expanding the reconstruction at some level of the resolution of the how much I want to see the overall size. Let me go back for 30. Yeah, it's a good number. Action. Let me load now my HSA. Okay. Okay, so we have our sample there. Let me show something here. Surface transparency, 60%. So if you see here, the way that we overlay the map over the structure does not really show any agreement between what we expect to see the conformation of the crystal structure with my BD model structure that I'm calculating, right? So you need to do one superposition, the right superposition of our structure to our data. So the way to do this is you can copy our them fit here, which is the final fit for a folder. I already did that here, and use supercomp to do this superposition. Let's do that by clicking. If you don't know how to access those command lines here for those softwares, HSAX has a very nice documentation you can use to do whatever you need to do. Let me see. And here is the online version. I don't want the online version now. Let me. I can go back there later. So you have the HSAX softwares here on the HSAX spec page, and you can look what software you are using. Let me see what is the one. Oh my gosh. Supercomp. Okay, they are not using Supercomp anymore. There's a new software, but they still can use Supercomp on HSAX. They are changed, replaced by SIF. Does the same. Does the same. Does the same thing. That is the superposition. I'm gonna call supercomp. You probably can use supercomp as well on where it sucks. If not, let me know. We can see what we can do. So let's call the command line here on our Windows computer, and we're going to do the superposition. So we assess the folder, cd. Okay, I'm the folder where I have my the files that I want to do the superposition. So I'm gonna first call subcomp, superposition computer, subcomp, is that right? Comp is with B, superposition combination, yeah. And the first PDB, so we look there, we have HSA monomer, okay. HSA monomer, and you do the superposition. You use the as underscore as, and you can tab, and you're gonna see the file you need to fit. So this command is gonna superpose the monomer of HSA with your dem fit ab initio reconstruction, and you just need to press enter. It's gonna start for you to do the calculation. It's kind of fast. The results of this superposition is the file with R in the end. So this reconstruction here was already moved to the so already superposed to the HSA. Now you can overlay those two structures together and see how they look one over other. I'm gonna call my chimera back again. Okay. That's too much. File open. I think I'm already on that folder. So let's start loading our move it PDB, which is my ab initio reconstruction. Okay, so I can definitely now generate the map. Okay, so again, the command to generate the map in Chimera is mol MOL and then you say model 0, and the resolution you want is 30 angstrom, which is okay. You can tweak that, you can tune that later. Okay, so next now we can open our crystal structure here. Open. So HSA. So the crystal structure now, as you see, it's nice fit inside of the envelope, and you can just make that a little bit fancy. We can have a white background, and you come with the surface to I say 70% of 70% of transparency, and you can model pane. You can now hide some modes that you don't want to see. For instance, the initial ab initio, because we are just looking the map of the overall map from the reconstruction. As you see here, the ab initio reconstruction recover very well the shape that we expect for the HSA. So the N-terminal region and C-terminal region, they are well fit inside the map. So that tells you have a good reconstruction of our data. That is a very well nice representative of the overall conformation of our data. So that is you already have a figure ready for publication here. And you definitely can use it. Chimera, you can definitely do more things to visualize, do different um, um, colors for the second structure, but that's not my my aim here now. Okay, so I think I covered what I want to show for the ab initio reconstruction, and let's go over uh, comparison with crystal structures. Okay, I want to go over the sites back here again later. Okay. Okay, I'm talking about crystal structure, right? I'm not sure if everyone is familiar. Probably who is the a person that work with proteins know we're looking for PDB structures, but for those that maybe is not that familiar with the field and wants to know, so you can Google for PDB database, and you can find the crystal structure you are looking for there. Looking for the name of a protein, Roman zero albumin. Okay, enter. So you have a different uh, types of protein, different conditions where the protein was crystallized. You can just using, for instance, this one here, also in 1999. Sorry, some more. Also in 1999, and you can download the PDB file. You can download the PDB file and also the sequence of our protein, and then other types of files that comes together that is made useful to you, help you analyze your data. If you have a biological assembly is not, or protein is not really the monomer of, is not the biological assembly, is not the functional unit, so you can download this biological assembly here and use as a PDB file later. Okay, so this is one way. Now, now that we have the crystal structure in hand, we want to do the comparison with our sketching profile, right? So that is where chrysone is the one that plays a big role here. And then you can, again, using the command line of the HSACs to do this comparison. You can also do this uh, crying calm chrysone uh, of the offset of the command line, but I I think personally I think it's just more work. You can definitely uh, um, just type two comments here and you get to our sketching profile. So now what I'm going to do is going to change the folder where I am for Chrysome Fit, which is also on my folder for the workshop. So I'm going to Chrysome Fit and okay, so cd okay, so I'm directly my command prompt to that folder, and here is very simple as well. I'm just gonna call Carson, and first file is my PDB, which is HSA. Oops, did not go HSA. HSA underscore. Okay, it does not. It's gonna get other things. I'm in the right folder. Yes. HSA monomer one.pdb, and you fit again var subtract data as s underscore s. Okay. Now one thing you need to do is say what was the D2O buffer you are studying that sample. So you can just say slash D2O slash dash D2O, and there was 100% D2O. And it's 90% D2O is 0.9, and similar for the other D2O contents. You just press enter. Okay, so you already have the some results of the fitting here. You can see the chi-square, and you can see the RG from the slope of the intensity of the fitting, 24.94, which is very similar to what we saw before. So what is the output of the RG? There's one more thing here, just in the command line. If you are using adulterated sample, you have to say the period duration level of our sample here. So you have to specify for sample how much was the period duration, 85%, 100% of the tool for the tool. And then you have to specify here the period duration level which you having for more sample. So that is not the case here. For pre-8 samples, Chrison does the job to those calculations for you. You don't need to worry about. So the output is gonna be basically 3 files. Is the fitting here. Okay, is the fitting. So the results of the output from the Chrison, you can see here, is gonna tell you how was calculated. You can using different harmonical sphericals to fit your data, so you can adjust those fitting here. And let me see. Here are some outputs of the Chrison. You want to make compare the RG of the atomic RG and the RG from the shape. What else we have here? Okay, so and here is probably the chi-square of the fitting. Chi-square of the fitting. And it's pretty much what you want to get from this output here. Okay, how visualize the fitting back, right? One way is just go to raw back again, and you just load the fitting. Okay, I don't need any more of this data here. I'm gonna remove all of them and try get the fitting here. Create some fitting. Okay, select folder. Okay, monomer fitting. Okay, so if I use the second window here, I have my entire fitting there. You can see the blue data is my experimental data, and no, sorry, okay, let me change the fitting to something red. Yeah. So my fitting is the red curve, and then my experimental data is the blue curve. You can see there is a very nice agreement between both, right? One thing that I used to do as well, it's compare how is the P of R of my fitting, or when I just do, you can also using Chrison to only calculate the P of the scattering profile with no fitting, right? So you can see how it looks like a comparison between the structure with wire scattering profile. Just do the comparison. That is some important step before the meantime. Um, you start your experiment and you have some structure. It's good for you have a simulate structure of your experimental data, so you can have some ideas or clue what you should expect it, what is the shape of the curve, and how it looks like the curve if your data does agree with what we expected. You can do that using Chrison as well. Let's see now we want to simulate the HSA monomer in 100% of the tool, right? So minus D2O, 1. And then we just all ask to do the calculation. So now Chrison is going to give me a new output, which is the same, the structure is the same, but now it's number 0, 1. So I'm just Gonna load it, just fitting 01 here. 01 is there. Let me see. Yes. This is what I expect to see. Oh, from the calculated sketching profile of HSA. So then you can definitely compare with or let me see, yeah, if I'm right. Let me just double check if there's yes. Yes, we have the Q range and the intensities there is what I'm expecting to see. You have the calculation of the scattering intensity, and you can definitely compare what to expect to be the experimental data, which is that blue curve here. So in that way, you have a feeling of what you expect to see of our data. And even though you can, again, come here and do the Guinea fitting, you're going to get some feeling of what to expect to see the Guinea regime of our model. So that way you can calculate the Guinea of our model. So you can know what you should see in our data. And you can also do the P of R in a similar way. P of R. And you can say, okay, that's look good. Okay, what else? Let me see. I did Cresson contrast very series, so we're gonna let that by the last. So I put some data there. We can definitely work after I finish here, and we can talk a little bit more about the resource here. So if you want to use HSAX online, you can just register using your university account. You can have all of the softwares there, and they can run. You don't need to be using our computer or computer resource to be running the software. So um, all you more, like I say, is I'm not going to touch on that today, but it's for analyzing mixtures. You can do different kind of those things that I show you today. You can do that, include Cryson as well. Those are different softwares you can use to analyze sun's profile. I think now is if you have any questions, and you can start work on the data on yourself. And if you have any questions, I'm happy to help you. One good start point is the contrast variation series. So you can plot the contrast variation series and start doing the subtraction. And as your prognosis, I can show you what's going on. I can tell you what's going on and how you analyze the data. I'm still sharing. Yuki, Jacob, um, um, I don't remember that I saw that for nanoparticles. Those kind of analysis more for macromolecules. Nanoparticles in general, we do it's a shape dependent analysis. So in Sachs view, there's different kind of form factors there that you can use to model war data. And those kinds of ab initio shape, it's more reliable for those kind. They are built for those kinds of systems that more like molecules, RNA, DNA, those kinds of biological samples.
Yeah, I think one point would be that these approaches really need a monodisperse scatterer, right? And with nanoparticles, you probably have some level of polydispersity in those samples, so that you might not get a very accurate ab initio model using that approach. So yeah, I think more traditional approaches to apply geometrical shapes or those types of analysis to your system would be better. And Wellington, you've done some stuff with lipid nanoparticles as well, so that's sort of the approach you use there as well, like using ellipsoid form factors or dual compartment type systems. So yeah, you can talk a little bit about that.
Yes. Let me try. Let's see if I can find a presentation here. Second. Let me show you some construction here. So here is one case where we have the nanodisc, right? Which is the membrane scaffold. It's a little bit different. Oh no, it's not that I want to show. Sorry, I got a mess up here. Hold on. Okay, so that is more what I was planning to show. So here is more like a core shell structure that we have, which is maybe similar with a nanoparticle. And for those kind of sample, we apply a shape-dependent model. So we have structure factors for those structures that we can use to fit your data. So this is the best approach for you to those kind of fitting that we want to do. So you cannot really recover one ab initio reconstruction for those kind of systems because, like you say, they are not really monodispersed. So you need to use different approaches to fit your data. So the approach is using the form factors, and then the software most used to that is Saxview. Is one of them. I think in the other section, if you want, you can watch the Venk sessions as well. He probably touched on those types of fitting. So I know Jacob and Yuk, they have SANS data to analyze that was collected on BioSANS. I'm very happy to help them to go over the analysis and see. I think now you guys have some ideas where to go and the resource you can have to to try analyze those types of data and what information. So I did a very try make it simple because my assumption was most of people doesn't have background on those types of analysis, and then from where to start, right? That was my initial idea, and that is mostly what we need to do during some more sophisticated analysis like molecular dynamic simulations and other types of uh, modeling of the structures demands much more time and depend of the system you are work with. But if you need help with toward that analysis, please reach us out. That we are more than happy to guide you and say what direction you need to go, and based on what we know of the system, which is also very important. So what I applying here was most for globular structures, but they also apply for known uh, disorder for disordered structures has IDPs as well. There's kind of difference how you properly analyze those kind types of data, but I think pretty much I cover uh, the basic there for you to start the data analysis. Uh, Probably tomorrow we will be working to separate the talks in each talk in individual uh, uh, formats, and soon we can have them ready. We can share with you. Uh, we can share with you all. Like you said, we're gonna send an email soon with links and everything. It's okay if you go stand. Um, what key range is going up? What's the region? Oh, you mean after the high Q?
Yeah, so basically at the high Q points, like I know like it should go down till the QRG, like whatever RG we are getting, and if we multiply it with by 0.3, so till that value it should go down. But what if it goes up again, like higher to those values? Is it like okay?
I'm trying to think the situation. So when you say the cracked pot, you are talking about the dimensional cracked pot or the regular one?
Like the regular one. So like what happened in my case many times, it's like when the data is noisy at high Q, and when I try to like subtract it and subtract the incoherent scattering, so it gets down even at like 0.115 or like in between range of like Q. So and after that when I do the Kratky, then it goes down um, till the QRG value. But then again, it's like starts going up. I'm not sure, like, does it make sense?
I think you have a different uh some different effects on word data in the high Q, right? That is a data you collect in Wikisons, right?
Yeah. But
Yeah.
yeah. Mm-hmm.
It might be easier to if you could see the data, right?
You can see the yeah. For me, it's gonna be hard
Um,
to tell you. So in the ideal case, you should not go up again.
like ideally, it should like go all the way down, I guess.
Yeah. So the in the small angle scattering region, you should see goes down, and then after if you go to a plateau region, right, you have no scattering. Then for very high angles, you should expect to see in the wide angle, you should see something comes up again, but that is a different effect. I think if you have some kind of incoherent scattering that's not really well understood, is some kind of extra affecting our sample, you should see some difference in the high Q, because that is not the contribution exclusively from this kind of type of incoherent scattering that we talk about.
Yeah, it might be, yeah, exactly. It could be an artifact of the measurement. So
Yeah,
defining what what your Q max is for where you're getting reasonable data is important, right?
Mm-hmm.
yeah. How noisy is the data there?
Like it is noisy. Like, yeah, like even before like 0.3 Q range in between. It's with like some of the samples, it was noisy, and then after doing the reduction, that was happening.
The sample was in the prorate buffer or was deuterated?
It was deuterated.
Deuterated. Yeah, that could be some kind of artifact. But in general, if you don't see, there's definitely some mismatching that you cannot really tell what's the. Maybe you can tell, but we need to look at the case close and see what is how much is going up and what is the issue. But you should expect for a protein the form factor, right? You have the shape, and then the for globular you should see a Q2 minus 4 decay on the high Q and not going up again. So there is no minimum meaningful information for you there that you can not really belongs to our protein data.
Mm-hmm. I have another question related to this. Sometimes, like in the Kratky itself, there are like two peaks, but that is okay.
It is. Let's assume. Let me load one. I have the data that I can show you. Oh, this yeah, and it should work actually. Take that one. Okay, so here is this. Don't want to show my error bar now. It's okay. So if you do the cracker plot here, so you see this cracker plot, you cannot this peak you cannot really remove it because it's where you have the oscillation, right? So let me make that bigger. So this is the most important ones which tell you the shape it's more globular. So that's goes down. But then you see the way it goes to the high Q. If you don't have the oscillation, probably our data here, you'll be going down to 0.04.
I don't think I'm able to see
No,
your
no. Let me
no.
stop
So
sharing. Can you see now?
yeah, I can see it now.
Okay. So let me put back here. So you see the shape of the cracker pot, right? You have
Yeah.
the main peak and you have a secondary peak there.
I think
But
you
that
should
is the
show the
log log.
Nidhi
Yeah,
saw your yeah, there's your scattering data,
yeah.
right? So this
Here's my scattering data. I have oscillation there on the high Q regime. These oscillations deviate from the Q2 minus 4, which is this regime here. So there you cannot really eliminate a 4 data because when you do the cracker plot, you are transform your data to other space, which is IDQ q squared by q, and then the oscillation is still there in the region because we cannot really remove. But if you don't have the oscillation, you see a peak, which is the globular part of the structure, which tell you is folded, and then you see that going smoothly to around q to 0.4. Does that answer your question?
Yeah.
It's normal, yeah.
Mm-hmm.
In case you can definitely see then there.
Okay. Thank you.
Oh, no problem. Okay, I think we are almost close to finish our hands-on section. Thank you everyone for time to join us and participate of our workshop. We are very happy to have you all here. If you have any questions or go over the data, please, if you have any questions, reach us out. We are more than happy to help you analyze the data. If you have collected data, you are struggling to interpret the data, we are happy to give some guidance on what you can do. And there is other softwares as well. I do not cover everything here. There is Dense that does also miniature reconstruction for the sun's data. It's a new feature that we can use. I think Nidhi, she's already using that software. Um, we are more than happy to help you all. Hugh, do you have any words?
Yeah, I think yeah, not really. Thank you everyone for sticking around for the second day as well. Hope this was useful to you. So as Wellington said, that we'll try and get well, hopefully we can get them done by tomorrow. It might take a little bit longer than that. I'm not sure how much work's involved in editing them. And the other thing we'd like to do is send out a survey to you guys, and we'll definitely try and get that out to you by tomorrow. There's a question about sharing the presentations. We will put all the presentations on our website with the recordings. So, and we can do it separately, and that might be we might be able to get the presentations up before the recording. So they'll be made available to you at the CSMB website. Okay, and that's it. I think so you can expect an email from us if you need any help with beam time proposals over the next couple of weeks. Please reach out. If you need any help with data analysis for data you've collected, as Wellington said, we'd be more than happy to help you out there as well. Will no, won't. It will not, Jacob. Our CSMB website is public. Okay, so you won't need that. Okay, thank you everyone. Wellington, I'll let you say the final goodbye.
Yes. Thank you, everyone. I hope you see next year again. We're definitely gonna plan to do next for the workshop. This was the first one, and so again, thank you everyone to join us.
Thank you.
Thank you. Thanks, guys. Have a good one.
Okay, Wellington, I'm going to sign off. Thank you.